Welcome back. The world is made of molecules, mostly molecules that have carbon in them. So, organic chemistry is largely the chemistry of carbon-containing molecules. So let's think about bonding with carbon. The carbon atom. If we look at its valence electrons, where are those valence electrons in a carbon atom? Well, we've got a 2s orbital. Again, that's kind of a sphere-looking thing. We've got 3 2p orbitals. P orbitals are kind of these figure-8 barbell-looking things. We usually think about them along the Cartesian axes, x, y, z. So these are the valence orbitals of a carbon atom. Cool. So what do carbon molecules look like? Well, carbon molecules, like methane here, are generally tetrahedral, right? So they are three-dimensional. They're kind of this pyramid-ish shape, right? So kind of like that. So that's cool. That's 109.5 degree angles, all of them. Okay, so mental map. How should I think about that bonding with these orbitals, right? Try to superimpose your Cartesian XYZ over this beautiful tetrahedron. I can kind of see it, but like, okay, my z-axis, y, doesn't really work, and it's not helpful. It doesn't really help us understand bonding in the molecule. So here's what we're going to do. These orbitals are kind of a math trick in some way, and we can combine these orbitals and come up with a new set of orbitals that will help us describe bonding more accurately. And again, as an organic chemist, that's why I care about orbitals. I care about orbitals to the extent they help me explain and predict stuff. Okay, here's what I'm going to do. I'm going to take these 4 orbitals. I'm going to put them in a blender. Put a cap on it. Cap. Broke, right? Go in there, fix it. Okay, so now 4 orbitals, 3 in 1. Now, instead of ending up with 1 lower energy spherical and 3 higher energy, I am going to end up with 4 orbitals of equal energy. Okay, and that each of these is going to get one of carbon's 4 valence electrons, and I can think of each of these as essentially being on one of these tetrahedral axes. So they're kind of like lopsided figure 8s. And again, this is telling me where the electrons are. So now in my new system, I've got sort of my orbitals pointing along the bonds that I have and expect to have in the tetrahedron. Okay? So we're going to call these sp3 orbitals because they are made from 1s and 3 of the p orbitals. We're going to call this a hybridized orbital. Right? We're hybridizing s and p orbitals to come up with an sp3 orbital. We're going to use it a lot like we used that sigma orbital in making bonds. So for instance, looking at a CH bond in methane, something like this, I'm going to take one of those sp3 orbitals from carbon, right? And I'm going to take my s orbital from hydrogen. And just like before, 2 atomic orbitals are going to come together to give me 2 molecular orbitals. And it's okay if the 2 orbitals are different energies. They usually will be, right? Unless it's the same atom, perfectly symmetrical coming together. Just as before, I'm going to make sigma and sigma star orbitals, bonding and anti-bonding orbitals. What do they look like? My sigma orbital more or less, again, looks like the orbitals are mixing together very well. So here, the big lobe of my carbon is pointing over my hydrogen. They're kind of all fused together. It's really just a big blob of electrons here with a little bit of a sort of a back lobe of that carbon. So that's what a sigma orbital looks like with this sp3 orbital. The sigma star orbital now again has a node in the middle where there is no electron density. We've got a lot of the electron density is outside the atoms. And this is, again, anti-bonding in the truest sense. if I put an electron in that bond, or if I forced one of these electrons to go up here, it would help to take that bond apart, help to destroy that bond. So sigma bonding in organic molecules using hybrid orbitals like this looks just like making sigma bonds from simply two s orbitals, like in H2. With sp3 orbitals, now we can start to understand the bonding in molecules like methane that have tetrahedral carbon. And that's the point, right? We're trying to describe the world we see around us. We need tools to describe that reality, and orbitals is one thing. Now, unfortunately, there are lots of molecules that don't have this tetrahedral geometry. There are lots of molecules that have trigonal carbon that has 120-degree angles. We often see this with this double bond. And there are other compounds that have just a linear arrangement, where we have essentially what we call a triple bond and a 180-degree bond angle. So we need a system that's going to help us not just understand bonding in tetrahedral things, but understand bonding in molecules like look like this. Okay, here are carbon's atomic orbitals. We've got one s orbital and three p orbitals. Again, we usually think about this as along the axes, x-axis, y-axis, z-axis. So last time when we were setting up our tetrahedron, we just said, let's put all four of these in a blender and mix them all up and deal out the cards again, and we'll get four equivalent sp3 orbitals. Remember, we called it sp3 because it took all three of these p orbitals with it. Here I've done something different. I've kept one p orbital the way it is, and I've hybridized the other two p orbitals along with the s. So now I have sp2 orbitals. What does that look like? It looks like this. The hybridized orbitals, the sp2 orbitals, more or less look like sp3 orbitals. They have that same kind of lopsided figure 8 motif. But in this case, instead of being along the axis of a tetrahedron, they are in the same plane as the atoms. Okay? So again, our system, the way it's set up, has our orbitals along this sort of trigonal planar geometry. So then where's the p orbital? The p orbital is then kind of above and below the plane. If we take this wedge as coming out at you and this dashed line is coming back toward me, now this is flat, and my p orbital is kind of above and below the plane that the atoms set. Okay, so hybridized orbitals, the sp2 orbitals, are between the atoms in that plane. The p orbital is above that plane. And that's what a double bond is. A double bond is one sigma bond that is two sp2 orbitals overlapping, and it has a p orbital out of that plane that is also overlapping. When we say double bond, then, we don't mean two of the same kind of bonds. We mean one sigma bond that is caused by overlap of these hybridized orbitals along the axis of the bond, and one pi bond made from two p orbitals overlapping. So if we look at the molecular orbitals of this ethylene molecule, we've got that carbon-carbon sigma orbital lower in energy, and this pi orbital, overlap of pi bonds, higher in energy. Why is that? Why are sigma orbitals more stable than pi orbitals? It has to do with orbital overlap. As you can see here in this sigma orbital, these sigma orbitals are overlapped really, really well. They're really on top of each other. And that strong overlap leads to really kind of efficient sharing of electrons and a more stable orbital. Here, this pi orbitals, they don't overlap quite as well. Notice that they're not really pointing at each other. If they're overlapping, it's more or less because I've drawn these things a little bit too small. Right? So they're kind of overlapping enough to make a bond, but they're more diffuse, they're more spread out, and they're kind of less on top of each other. Better overlap means stronger bond. Stronger bond, again, meaning harder to break, lower in potential energy. So in this molecule, my highest filled MO is probably this pi orbital. My lowest unfilled MO is going to be the pi star orbital. So if you remember, sigma orbitals have sigma star orbitals where anti-bonding. What would an anti-bonding orbital for this pi orbital look like? Like this, right? So now, just like here, we talked about phase or the whole color or not color thing. So here, I have electron sharing between this lobe and this lobe. Notice that in a pi orbital still, there is a node in the middle. So in the plane of the atoms, there actually is no pi electron density. In the pi star orbital, not only do I have that plane node, I also have a node between the atoms. So there's no electron density between and on the plane. Okay? And notice that they're a little bit canted out, because remember, if orbitals can't overlap, then they're actually repelling each other, just because electrons and electrons repel each other. They're both negatively charged. So this is what a pi star orbital looks like. This is what a pi orbital looks like. And so when we talk about breaking a pi bond, this would be the distance in energy that we would need to bump that electron up to. And of course, above this pi star orbital is probably our sigma star orbital, which is simply these things reacting, or these things combining out of phase. So this energy gap between highest filled and lowest unfilled orbitals is a pretty important thing. When we talk about things absorbing light, this is generally what we're talking about. So something absorbs light when that light photon has this much energy in it and can promote this electron up to this level.